Hello, this is Dr. K, and we are continuing this week's module on software and software engineering based on chapters 1 and 2 of Software Engineering, a Practitioner's Approach, 8th edition by Roger Pressman and Bruce Maxim. In the last video, I gave you some tips for reading Pressman. Remember the themes of quality and change. In this video, we're going to spend some time trying to answer the question, what is software? So, what is software? Well, maybe we think we know it when we see it, but can we articulate it? Suppose you had to describe software to a child who knew what a computer was, could use applications on a computer or mobile device, but they just weren't sure what you meant when you used the word software. What would you say? How would you describe it? Maybe you'd say something like, the programs on your computer are a kind of software. Or would you say something like, software is what makes your computer work? Or maybe you'd say, software is what tells your computer what to do. I think all of those are interesting responses. Let's see what Pressman can contribute to these. According to Pressman, software consists of instructions, data structures, and documentation. Now, I'm not going to talk about documentation. That's somewhat debatable, and we can save that for the discussion boards. But I do want to talk about the first two bullets, instructions and data structures, because I think there's something interesting here. When we say software tells your computer what to do, I think it's implied in that software is a set of instructions for the computer. What people sometimes miss is that data is also part of software, and that storing and manipulating that data in meaningful ways is what makes software so effective. In the early days of computing, there were machines constructed in such a way that instructions and data were stored in physically separate locations and accessed separately. This architecture, called the Harvard architecture, did not catch on. Some people believe that if it had, it would be much easier to guard against certain types of cyber attacks, where something masquerading as data turns out to be a set of instructions that is later executed by the CPU. Another interesting story in the relationship between instructions and data occurred in the 1960s, when some folks created a language that encapsulated the data with the operations that manipulated that data. Can you guess what kind of language this was? The name of the language was CS57, and it was the first example of an object-oriented language. A question related to what is software is, what does software do? We've already talked about the relationship that software has with data and information. So at its most fundamental level, we can think of software as something that transforms or manipulates information. One of the things that Pressman emphasizes regarding the nature of software is that it has a dual role. It serves two different purposes. The first is its role as a product, as applications on computers and mobile devices, and as programs that control hardware and networks and embedded systems. And the second is its role as a vehicle for delivering a product, as operating systems and drivers that control other programs and affect communication, and as compilers and development environments that help build other software. Regarding transforming information, the only thing I would probably add to this list would be the storage of information. A good way to understand what software is to compare it to hardware. When we talk about hardware here, we're not just talking about computer hardware. We're talking about physical systems. For example, a shovel is a piece of hardware. A table is a piece of hardware, and a toaster is a piece of hardware. Before I proceed to the next slide, let's think for a moment about how software might differ from a physical object. Software is virtual, not physical. You can't see it, touch it, or smell it. And what are the implications of that? What are the implications of that when it comes to producing software? What are the implications of that when it comes to using software? Okay, let's look at what Pressman says. Pressman gives 4 differences between software and hardware. However, I have to warn you that this is not something you will find in the 8th edition of the book. In fact, the last difference here, that software is inherently more complex than hardware, was dropped way back in the 6th edition. And 2 more, manufacturing versus development and components versus custom built, have been greatly de-emphasized in this 8th edition. But I think it's instructive to include them in these slides because I think it leads to a lot of good discussion on the discussion boards. Let's look at these one by one. We say that hardware is manufactured because the costs involved in hardware have been traditionally associated with producing the physical product. Yes, hardware does need to be designed, but once designed, you still have to pay for the materials and the labors to make that product. In contrast, there's no physical product associated with software. All of your costs are in design. You might argue that coding is more like production than design, but you're still not constructing something physical. One point that brings this home is in the second bullet. Adding more people to an already late project can actually slow things down. Why would this be? If I gave you 10 seconds to think about it, or you can pause the video if you want, can you tell me why adding more people to a software project might actually slow things down? I'll give you 10 seconds starting now. Okay? Well, one of the big reasons for this is that since software costs, not just in terms of money, but in terms of time, are focused on design. If you bring new people onto a project, you have to bring them up to speed on the design of the software, which in turn means taking time away from the current developers, who could be working to get the project out the door. In manufacturing, learning how to put components together or how to operate a machine on an assembly line is not as time-consuming as learning the design of a software system, although the cost and time will go up as the complexity of the hardware system increases. Another distinction between hardware and software that Pressman does talk about in the current edition is the one between wear and deterioration. The vertical axis here is the failure rate. So the higher you go on the vertical axis, the more likely your product is to fail. The horizontal axis is time. A typical failure curve for hardware looks like this. It's often called a bathtub curve because it looks like the cross-section of an old bathtub. The high part of the curve at the beginning indicates infant mortality. This is reflective of defects in the manufacturing process. If there was a defect, your hardware is likely to fail relatively quickly. If it does not fail, the hardware will work for a period of time with a very low risk of failure, until physical wear and tear take its toll and the hardware begins to wear out, as indicated by this high part of the curve at the end. Software is virtual, not physical, so it doesn't have any parts that can wear out. That means that ideally a software failure curve would look like this. The initial infant mortality portion of the curve is due to bugs in the software, But as those bugs are discovered and fixed, the software is less likely to fail. Now that's the ideal case, but it's not what happens in practice. The actual failure curve of a piece of software looks like this. So why does the failure rate rise in practice? The reason comes from one of the main themes in the Pressman text, and that reason is change. Because of major changes that are introduced to the system, the software must be modified. When the software is modified, more bug fixes are introduced, and again, it takes time to fix those bugs. Before you can fix your software so that it's working as well as it was before the last change was introduced, another change is introduced, and the whole cycle starts over again. When this happens, we say that the software deteriorates. When the software deteriorates so much that it's practically unusable, we start over. For example, Windows 7 was almost a complete rewrite of the operating system because it was becoming so difficult to maintain. So change is the culprit. But why does software have to change? As this is a major theme in Pressman, please pause the video and take a moment and think about what some of the reasons might be that software would have to change. Are you ready? Let's see how many things you came up with that match up with what Pressman has to say. We've already talked about the need to fix bugs or errors, but that's not typically a change that will cause the software failure curve to peak. The most common reason that software has to change is to accommodate new features or new requirements. This can lead to something called feature bloat or requirements churn. The other reasons for change that you see here have to do with changes in the environment that the software resides in. For example, maybe the operating system gets updated and your software has to be updated to better interact with the new operating system. Or maybe your software depends on other software, like a database, for its effectiveness. If that database is updated or replaced, you need to update your software accordingly. For all of these reasons, software has to change. In the current edition of the book, Pressman discusses these changes, other than the bug fixes, within the context of legacy systems. One of the things that Pressman emphasizes about legacy software is that sometimes the best approach to a poor quality legacy system is to leave it alone until you're forced to change it due to one of the reasons listed on the previous slide. One area that software lags behind hardware in its use or reuse of pre-built components. In hardware, there are many components that can be put together to create new products. From standardized nuts and bolts to home theater components that plug and play with each other fairly easily, to standard-sized doors and windows for your house that you can pick up at your local home improvement store. But software does seem to be moving in that direction. If I give you 10 seconds, can you think of one example of a small software component that's often reused, and one example of a large software component that's often reused? We'll skip the medium-sized component for the time being. I'll give you 10 seconds starting from now. Okay, here are the kind of components I think of in these categories. For small components, I usually think of a class in the Java library. No one who programs in Java would write, say, a list from scratch. They would use the list from the Java library. Pre-built GUI components are another type of component I put in this class, though some of these can have quite complicated functionality. Like the text areas in Java, you can cut, copy, paste, change fonts, and even render HTML. For large components, I typically think of COTS or commercial off-the-shelf products. Almost no one would write their own database from scratch nowadays. They would simply use something like Oracle or MySQL. Medium-sized reusable components seem to be used within companies that are doing, for example, product line engineering, which we're going to talk about later. But they don't seem to be used much between different companies. I think the important part of this slide is the last bullet, that the industry seems to be moving towards component-based construction. Perhaps that's why Pressman de-emphasized this distinction in the current edition of the book. Finally, regarding software complexity, Pressman no longer argues that software is inherently complex while hardware is not. That may be due to the fact that many hardware devices are becoming much more sophisticated and often comprise a mixture between both hardware and software. The person that really popularized the idea that software was inherently complex was a software engineer named Fred Brooks. He wrote an essay called No Silver Bullet, in which he argued that while we seem to be making order of magnitude improvements in building hardware systems, such improvements in software systems were not possible due to the inherent complexity of software. The essay will be part of this week's reading assignment. That concludes this video on what software is and what it can do. In the next video, we'll look at the different ways in which people go about categorizing software.